Thank you, Dan. I actually want to start with an apology if these slides look familiar. I accidentally stole Robert's theme from yesterday. I did that before, I promise. Great minds think alike. Anyway, I'm excited today. I'm Drew Haugen. I'm excited to present time warping for clustering picture deliveries, done in collaboration with Dr. Scott Powers of Rice University. So to open, I want to discuss the state of public baseball research on a few different fronts. On the pitching side, a lot of the really cool work that's being done relates to pitch modeling, and that's analyzing the stuff, command, and overall pitch quality. These metrics can be found at Fangraphs, Pitcher List, Baseball Prospectus, and others, and are commonly used by teams as well. Really cool work is being done with release angles to quantify pitcher command and the consistency of those angles. On the hitting side, a lot of really awesome work is related to the pitch modeling work that's being done, and adjusting hitter performance and hitter evaluation for the quality of pitches that they're seeing. Additionally, with the release of bat tracking data, as we've seen at this conference, we can get an idea of hitter process, approach, and talent. But on a third front, on the biomechanical front, we've seen a lot less research, and for a long time this came down to a lack of data availability. Biomechanics data was largely proprietary from labs, but in the past couple of years this has changed. Driveline Baseball has released some of their lab capture data in a really cool project called Open Biomechanics. In some of the biomechanic analyses we've seen, though, we've noticed a few main things that we think could be improved. One, largely these analyses focus on domain knowledge metrics, and in doing so, they reduce an entire sequence of data capture down to just a single row for each pitch or swing, etc. And we think that this can exclude information on how exactly players are getting to the different positions they're in, rather focusing on just a few main output variables. However, there are a lot of challenges when analyzing sequence data, mainly relating to alignment and the way that the data is captured. So we came up with a way to analyze these sequences fairly using time warping, which is a common technique in the time series community. And for this project specifically, we came up with a custom time warping solution to analyze pitcher deliveries. The way we do this is we define three main reference points: time equals 0 being peak leg lift, time equals 1 being foot plant, and time equals 2 being ball release. And with our reference points, we then take slices, evenly spaced slices of the sequence between these reference points. And what this allows us to do is to standardize and align these sequences so we can fairly compare pitcher deliveries to each other. The pitchers will be in a similar position to each other at the same normalized time, at the same time warped time. And additionally, this focuses on the most important data that we have. We're most interested in how a pitcher is moving between peak leg lift to when they release the ball. And obviously there's important information outside of that, but that's what we want to look at the most. So what we have here is two animations comparing a raw sequence to a time warped normalized sequence. So on the left, as you can see, the pitcher in blue has completed their pitch before the pitcher in red has even begun to make a move towards home plate. And so these two deliveries cannot be compared or analyzed because they're vastly different. On the right, we have the same two pitch deliveries after they have been time warped. And as you can see, throughout the majority of the delivery, they're at very similar points, which allows for a fair comparison or analysis. After we have our time warped pitcher delivery sequence data, we decided one use case would be to cluster together the deliveries we think are similar, or that could be identified as similar. And so we scaled this data and ran it through a hierarchical clustering algorithm, and what that outputs is this dendrogram here. And what this dendrogram shows is every pitch in our data set, and they slowly converge into larger and larger clusters. This dendrogram can be cut at different points to define a different amount of clusters. In this example here, we have 8. And as you can see on the left, there is one pitch in its own cluster, a few small clusters with 7 or 8 pitches, and then 4 main clusters. If we compare to the way that a lot of biomechanic analyses boil down data to just one row, this is what we get with that same data using just points of interest. And as you can see, the dendrogram is far different. In fact, the pitch that showed up in its own cluster in the first dendrogram is now in the most common cluster in this dendrogram. So what that tells us is that the information that's held by analyzing a full sequence of data is different from what we're going to see if we just look at a few main key points of interest and cut out a lot of the other information. One interesting takeaway is that with this sequence data and through the use of clustering algorithms and other analysis, we can identify things that as analysts or players who are removed, or people who are removed, from the coaching side, we can identify things that are unique that might not always be obvious to us. I know personally, I do not have a trained scouting eye, and this is the delivery that shows up in its own cluster when using sequence data. And outside of maybe an exaggerated arm swing, there's nothing apparent to me that makes this so unique. But through the use of our clustering algorithm, we can identify outliers and in conjunction using the entire sequence to identify outliers. So what are the takeaways of this analysis? What are some of the limitations, and what can we do going forward? Some of the takeaways, obviously, are that using the full sequence allows for a more encompassing analysis. We get more information, and we drop a lot less when we use an entire sequence rather than just a few main point of interest variables. And this sort of analysis has a ton of applications in baseball research and development and player development, especially in consistency and repeatability, whether that be through the use of clusters to see if pitchers consistently show up in the same cluster or near each other, or a different form of analysis, as well as in player comparisons, which are really common for coaches and especially for hitters in advanced scouting, comparing pitchers they will see to pitchers they have seen. This allows for a better quantification of player similarity. However, some of the limitations of this analysis are the small sample size. This data was made up of just 411 pitches, which makes it difficult, along with the lack of paired data, to make real broad conclusions. So as more data is made available, and as this biomechanics data is paired with ball tracking data, we can begin to make more conclusions. Going forward, possible improvements to this analysis are use of better non-custom time warping methods, including dynamic time warping, canonical time warping, and others. And additionally, finding ways to take model outputs like these pitcher clusters or outputs of different models and linking them to on-field performance are where we can begin to see teams get actual value and begin to then take this information and use it in research and development operations. I want to acknowledge SlidesGo for the slides theme. Y'all have now gotten to see 2 times. And Driveline Baseball for making these data available. Thank you.